If you compress the entire history of Earth into a single calendar year, dinosaurs would only appear on December 19th, the first humans, at 11 p.m. on December 31st. All of human civilization, from the first cities to today, is the last 10 seconds of that year. But here's what makes those 10 seconds remarkable. Scientists have introduced the term Anthropocene, a new geological epoch defined by human activity. If a future geologist were to examine layers of rock 1 million years from now, they would find a clear marker: a layer of plastic, radioactive isotopes from nuclear testing, a shift in the chemical composition of the atmosphere. 10 seconds out of 4.5 billion years, and we've already left a geological fingerprint that will last 1 million years. 10 seconds. And a geological mark for 1 million years to come. Now, what happened before us? From the very beginning. Before that, 4.5 billion years of events, catastrophes, transformations, moments that came close to ending everything. And most people know almost nothing about any of it. 4 questions. First, how many times was Earth on the edge of total destruction? And what saved it each time? Second, how did Earth rebuild itself? And why does it look nothing today like it did in the beginning? Third, what forces shaped the planet? And are they still at work right now? And fourth, why did Earth specifically become capable of supporting life? And could it easily have not happened at all? Let's start at the very beginning, at the moment when nothing yet existed. 4.5 billion years ago, where Earth orbits today, there was nothing, just a cloud of gas and dust slowly contracting under its own gravity. At the center of that cloud, the sun ignited, and the leftover gas and dust around it began to clump together. Smaller particles became larger. Larger ones collided and formed larger ones still. Gravity pulled everything toward everything else. The chaos of collisions went on for millions of years, and gradually, out of that chaos, planets began to take shape. The early Earth had nothing in common with what we know today. No oceans, no atmosphere you could breathe, no crust to stand on, just a molten ball of rock and metal, covered by a continuous ocean of magma stretching hundreds of kilometers deep, a planet burning from the inside and the outside at the same time. And at that moment, a collision happened that changed everything. Around 4.5 billion years ago, a protoplanet, roughly the size of Mars, slammed into the young Earth. Scientists named this protoplanet Theia, after the Greek Titaness, mother of the goddess of the moon. This massive object struck Earth and threw material into space that would become the moon. Picture the scale of that impact. An object the size of Mars, a planet nearly half the diameter of Earth, crashing into the young planet. The energy released partially melted both bodies. The debris thrown into space gradually clumped together. And as it cooled, it formed a single solid object, the moon. But why does this impact matter so much for Earth? And not just for the moon? Because the moon isn't just a beautiful object in the night sky. It's a planetary stabilizer. The moon's gravity holds Earth's axial tilt in a stable position, around 23.5 degrees. That tilt is what gives us seasons. And stable seasons give us a predictable climate. And to understand what that actually means, picture Earth without the moon specifically. Without the moon's gravitational stabilization, Earth's axis would wobble chaotically, anywhere from 0 to 90 degrees over millions of years. 0 degrees. The poles would receive sunlight year-round while the equator stayed in permanent darkness. At 90 degrees, the equator becomes the pole. Ice sheets would form and vanish over thousands of years. Oceans would freeze and thaw. No ecosystem could stabilize long enough for evolution to produce complex life. Mars, without a large moon, looks exactly like that. Empty, dead, unstable. Theia crashed into Earth and accidentally saved everything that would come after. But the early Earth was far from done with its chaotic beginning. The next 500 million years are known as the Late Heavy Bombardment. Asteroids and comets rained down continuously on the surface of the young planet, impact after impact. Each one more powerful than all the nuclear weapons humanity has ever built combined. The surface melted again and again. Any crust that managed to form was destroyed by the next impact. And here's a detail about our solar system that makes this personal. Jupiter's gravity deflects most of the large asteroids and comets coming in from the outer solar system, or captures them into its own orbit. Without Jupiter, the number of major impacts on Earth would have been several times higher. We saw this in real time in 1994 when comet Shoemaker-Levy 9 broke apart and slammed into Jupiter. 21 fragments over 6 days. Without Jupiter, some of those fragments could have reached Earth. Jupiter is still doing this, right now. But in the beginning, there was no protection, and Earth took every hit on its own. But it was exactly this bombardment that brought something critically important to Earth: water. The early composition of Earth during its formation didn't contain enough water to form oceans. The water came from outside, from asteroids and comets carrying ice and hydrated minerals. Billions of tons of water delivered by billions of impacts over millions of years. And if you want to feel that physically, look at a glass of water. A molecule of water sitting in your glass right now may have traveled billions of kilometers from the outer edge of the solar system. It could have formed on the surface of an icy asteroid in the Kuiper Belt, been knocked by Jupiter's gravity onto a trajectory that sent it toward the inner solar system, flown billions of kilometers, fallen onto the young Earth alongside thousands of other molecules, and 4 billion years later, ended up in your glass. The water in your glass is cosmic. It traveled billions of kilometers to get here, and the planet that received it began to transform. The atmosphere formed along 2 pathways: gases venting from the interior through volcanoes, carbon dioxide, nitrogen, water vapor, hydrogen sulfide, and gases delivered by comets and asteroids from outside. This early atmosphere contained no oxygen. It would have been lethal to any modern organism, but it held in heat. Around 4 billion years ago, as the bombardment began to ease, Earth's surface cooled enough for water vapor to start condensing. Picture this scene specifically. For the first time in the history of the planet, the first drop, the first rain in the history of Earth. But not the kind of rain that feeds fields. This was an acid downpour saturated with sulfuric acid, eating through rock. It fell on bare black basaltic surface with no plants, no animals, no microbes. The planet wept for the first time, and its tears corroded its own face. And from that corrosion, from that destruction, the first ocean was born. The first rain in the history of Earth. Acid. Alone. And from it, the first ocean. Dark. Hot. Acidic. Without a single molecule of oxygen. Without a single living cell. But already, an ocean. Already, a planet with liquid water. And that, as it turns out, is the rarest and most important thing in the entire solar system. Earth had taken its first step toward becoming something unique, but billions of years of transformation still lay ahead, and several moments when everything could have ended. The first ocean appeared. The first crust began to harden. The planet cooled enough for water to stay liquid on the surface. But Earth was only just beginning to build itself. And the next 2 billion years are the story of how the planet found a mechanism that no other known planet possesses. A mechanism that made it unique, capable of supporting life, capable of healing itself, but not without crises. Because the greatest crisis came from life itself. Why do mountains exist? Why do oceans exist? None of it makes sense without plate tectonics. Earth is a living planet in the literal geological sense. Its surface is not a hard, unchanging shell. It consists of several large and dozens of smaller plates that slowly move across the molten mantle beneath them, at a speed of 1 to 20 centimeters per year, roughly the same rate as human fingernails grow. And to understand what that actually means in concrete terms, human fingernails grow at around 3.5 centimeters per year. Tectonic plates move at roughly that same speed. Over a human lifetime, 75 years, the Atlantic Ocean has widened by about 2.5 meters. Right now, while you're watching this video, Africa and South America are moving apart, slowly, relentlessly, permanently. Where plates pull apart, new ocean floor forms. Where they collide, one dives beneath the other, sinks into the mantle, melts, and returns to the surface through volcanoes. Earth continuously recycles itself. And here's what makes this discovery particularly extraordinary. Almost everything unique about Earth is in some way connected to plate tectonics. Mars has no plate tectonics. Venus, almost certainly not. Mercury, no. Of all the planets we know, only Earth has this mechanism. And as recently as March 2026, a new study published in the journal Science shifted our understanding. Magnetic crystals have provided the earliest known evidence of plate tectonics, pushing its beginnings back by 140 million years, 3,480,000,000 years ago. Earth already had moving plates when the only life on it was microbial. But why do we need tectonics? What does it actually do for the planet? Here's the answer. Volcanoes constantly release carbon dioxide. CO2 is a greenhouse gas that warms the planet. But tectonics creates new mountains and new rock. Rain dissolves those rocks, and during that process, it pulls CO2 out of the atmosphere. That carbon enters the ocean, settles to the seafloor, and along with the seafloor, dives beneath the plate and returns to the mantle. A closed loop. Gets too warm. More rain, more rock dissolving, more CO2 absorbed. The planet cools. Gets too cold. Less rain, less CO2 absorbed. Volcanoes keep releasing gas. The planet warms. Earth has its own thermostat, and it's been running for 3.5 billion years. Plate tectonics doesn't just move pieces of crust around. It gathers them together and then tears them apart again, over and over, for billions of years. Throughout its history, Earth has had several supercontinents. Valbara, possibly the earliest, around 3 billion years ago. Kenorland, 2.5 billion. Columbia, 1,800,000,000. Rodinia, 1 billion. And the most famous, Pangaea, 250 million years ago. 5 supercontinents, and not one survived. But not because something went wrong. Earth is physically incapable of staying assembled. It always tears itself apart from within. Each supercontinent took hundreds of millions of years to form, and then broke apart under its own internal forces. Millions of years of gravitational pull to come together, and millions of years to break apart again. This isn't a flaw, it's a built-in mechanism. Every breakup changed the climate. Ocean currents reorganized. New shallow seas appeared between drifting continents. The climate transformed. And every transformation either opened new possibilities for evolution or destroyed old ecosystems. Earth tears itself apart from within. And every time it does, something new emerges. But one of those breakups caused something nobody expected. Around 715 million years ago, Earth did something that seems impossible. It froze. Completely. From pole to pole. To feel what that actually means, picture a specific place, where Hawaii is today. The tourist beaches, the palm trees, the warm ocean. 700 million years ago, there was a kilometer of solid ice, where the Caribbean Sea is now, a solid sheet of ice. The equator, not a warm belt, but the coldest desert imaginable. Minus 50 degrees, even where people walk around in swimsuits today. A kilometer of ice over the tropics. And the mechanism that triggered it was simple and merciless. The reflectivity of the surface, the amount of sunlight bouncing back into space, reached its maximum, which cooled the planet further, which created more ice. A closed loop that seemed impossible to break. Snowball Earth. And it didn't happen just once. At least 3 or 4 times, Earth froze completely. How did it start? The breakup of the supercontinent at Rodinia pushed enormous land masses above sea level. Tropical rock weathered intensely under the rain. That process pulled carbon dioxide out of the atmosphere too fast. The greenhouse effect weakened. Temperatures began to fall. Ice spread from the poles. White ice reflected more sunlight than dark ocean, which cooled things further. The planet fell into its own trap. But even here, Earth found a way out. Volcanoes didn't stop. They kept releasing CO2 even beneath a kilometer of ice. But since the surface was covered in ice, rain barely fell, and the carbon dioxide couldn't be absorbed. It accumulated in the atmosphere for millions of years, until its concentration reached 300 times higher than today. And then the greenhouse effect melted even the kilometer-thick ice. In a relatively short geological window, the planet swung from minus 50 to plus 50 degrees. The most extreme warming in Earth's history. Acid rain, dissolving rock, nutrients pouring into the newly thawed ocean. And after every thaw, an explosion of new life. The greatest climate catastrophe in Earth's history turned out to be one of the main drivers of evolution. But before Snowball Earth, there was another moment that changed the planet forever, and life itself caused it. Around 2,300,000,000 years ago, cyanobacteria dominated the oceans, the first organisms to master photosynthesis, splitting water with sunlight and releasing oxygen as a byproduct. And the most terrifying part is that the cyanobacteria had no idea what they were doing. Billions of tiny organisms just living, absorbing sunlight and releasing oxygen. For them, it was a perfect way to exist. They had no idea that oxygen was poison to everything around them. No idea they were changing the planet's atmosphere. No idea they were destroying most of the life on Earth. They were simply being themselves. And that was enough to trigger the greatest ecological catastrophe in the Precambrian history of the planet. They just existed. And that was enough to wipe out most of the life on Earth. For most organisms alive at the time, oxygen was poison, lethal. It destroyed their cells, the same way rust destroys metal. The atmosphere and oceans that had contained no oxygen for billions of years gradually became saturated with it. Most living things that existed before this simply died. The first mass extinction in the history of Earth. Before the dinosaurs, before fish, before any multicellular life at all. And that's not all. Oxygen destroyed methane, another powerful greenhouse gas. Without methane, the planet cooled, which likely triggered the first Snowball Earth episode. But those that survived learned to breathe oxygen. And oxygen-based respiration turned out to be so much more efficient than the alternative that organisms which mastered it gained a colossal energy advantage. 16 times more energy from the same amount of food. 16 times. But what does that mean for you personally? That difference in efficiency, and nothing else, is what allowed brains to develop. Neurons consume enormous amounts of energy. Without oxygen-based respiration, a brain is simply impossible. Your brain exists because microbes 2 billion years ago poisoned the planet with oxygen. The greatest ecological catastrophe in the Precambrian history of Earth, and the direct consequence, is you. Right now, as you think about this, you're using a mechanism that exists because of the greatest catastrophe in the Precambrian world. Earth transformed a crisis into an opportunity, as it always has, as it always will. Earth survived its birth in chaos, survived freezing, survived the oxygen crisis. It learned to regulate its own climate through tectonics and volcanoes. And now, a new chapter was beginning. Earth wasn't just existing, it was transforming, again and again, through catastrophes, through extinctions, through resets that each time opened new possibilities. 5 times, 5 great crises, 5 moments when Earth stood on the edge of becoming a dead planet. And every time, it survived. But every time, it came out different. The Ordovician period. Earth covered in shallow, warm seas. Almost all complex life lives in the ocean. Almost nothing on land yet, but in the seas, an explosion of diversity. The late Ordovician extinction wiped out between 49 and 60% of marine genera and nearly 85% of marine species. What happened? Earth cooled sharply. Glaciers spread. Sea levels dropped. The shallow seas, where the richest life existed, simply disappeared, dried out, and everything living in them died along with them. But within a million years, new organisms filled the emptied niches, different ones, more diverse. Earth rebooted. The Devonian period, the age of fish. The oceans teem with life. On land, the first forests and the first 4-limbed creatures crawling ashore. And again, catastrophe. The Devonian extinction stretched across 20 million years and killed 75% of all species on Earth. Forests were killing the ocean again, just as they would later in the Permian. The explosion of land plants changed the global climate and flooded the oceans with nutrients. Oxygen vanished from the depths, reefs disappeared, most marine life died. But after this extinction too, Earth came back. And now, the worst of all, what scientists call the Great Dying, the Siberian traps. Volcanoes erupting for tens of thousands of years. The lava field, larger than modern Australia. Billions of tons of carbon dioxide poured into the atmosphere. Ocean temperatures in the tropics climbed to 40 degrees Celsius. Oxygen in the water vanished. Acid rain destroyed forests. The ozone layer nearly disappeared. 96% of all marine species and around 3 out of every 4 land species died. Earth's forests were obliterated and didn't fully recover for another 10 million years. Earth almost gave up, but not quite. Those that survived were small, adaptable, flexible. They inherited an empty world, and from them, a new era began, the age of dinosaurs. Even after the dinosaurs appeared, they still had to survive one more extinction before inheriting the Earth completely. Pangaea, the supercontinent that had gathered all land masses into one, began to break apart. The Atlantic Ocean was only just opening. New volcanic activity along the fracture lines. New gases in the atmosphere. A new crisis. Around 80% of species disappeared. The dinosaurs' competitors, large crocodile-like reptiles and the primitive mammal-like animals that had dominated the Triassic, were gone. And the dinosaurs finally had an empty planet. They ruled it for 165 million years. But before we get to the most famous extinction, there's a moment worth picturing concretely. A Tyrannosaurus is living an ordinary day, hunting, eating, maybe resting. It doesn't know that 70 seconds before the end, an object is entering the atmosphere that will change everything. It doesn't know it's one of the last representatives of a dominant life form that has ruled for 165 million years. It's just living. And all that evolutionary success, all those millions of years of perfection, gave no warning, no protection. 165 million years, no warning, 70 seconds, and it was over. 66 million years ago, something fell from the sky. An asteroid roughly 10 kilometers across entered the atmosphere at 20 kilometers per second. It struck the area of what is now the Yucatan Peninsula in Mexico, the Chicxulub crater, 180 kilometers across. The energy released, billions of times greater than the most powerful nuclear weapon ever built. But the impact itself wasn't the main killer. Billions of tons of dust and soot rose into the atmosphere and blocked the sun. For months, possibly years. Without sunlight, photosynthesis stopped. Plants began to die. Herbivores followed. Predators followed the herbivores. But there's an important detail that often gets skipped over. The Deccan traps. Volcanoes in what is now India had been erupting for millions of years, both before and after the asteroid impact. It's possible the extinction had already started before the asteroid hit. The asteroid simply delivered the final blow. Around 75% of all species disappeared, including the dinosaurs, but not the birds. Because birds are dinosaurs, the only lineage that made it through. And not the mammals either. Small, hidden, adaptable, who now inherited an empty Earth. Let's step back, between the third and fourth extinctions, to talk about the event that shaped modern geography. 250 million years ago, all the continents were gathered into one, Pangaea, a single supercontinent surrounded by a single global ocean called Panthalassa. But 200 million years ago, Pangaea began to break apart. First, into two large pieces, Laurasia in the north and Gondwana in the south. Between them, a new ocean opened, the Tethys. Then Laurasia split into North America and Eurasia. Gondwana broke into South America, Africa, Antarctica, Australia, and the Indian subcontinent. India moved at 15 centimeters per year, the fastest movement of any continental plate in geological history. Over 70 million years, it covered more than 5,000 kilometers. The energy of that collision raised the Himalayas. And here's the thing, it hasn't stopped. The Himalayas are still growing, roughly 5 millimeters per year. Everest today is 17 meters taller than it was 100 years ago. The highest mountain on Earth is still rising. Plate tectonics hasn't stopped. It's happening right now beneath your feet. Everest is growing right now, 5 millimeters a year. Plate tectonics isn't something in a textbook. It's a process happening under you while you watch this video. And the breakup of Pangaea changed everything. New oceans shifted ocean currents. New mountain ranges created new climate zones. New isolated continents set off the evolution of unique life forms on each one. Kangaroos in Australia, sloths in South America, elephants in Africa. Plate tectonics doesn't just move continents. It creates new conditions for evolution. But there's a detail about the next supercontinent that changes the picture. In 250 million years, the Atlantic Ocean will close. New York and London will become part of the same continent again. But in 250 million years, the sun will be 10% brighter than it is now. Earth will be hotter, possibly too hot for liquid water. The new supercontinent may be uninhabitable. Plate tectonics saved Earth for billions of years, and billions of years from now, it may make it uninhabitable. The longest irony in the history of the planet. 66 million years later, the mammals that survived the asteroid evolved into thousands of new species. Among them, great apes. Among them, humans. Humans appeared around 300,000 years ago. That's less than 0.1% of the time since the first dinosaurs appeared. A tiny instant in Earth's history. But in that tiny instant, humans became a geological force. We changed the composition of the atmosphere. CO2 levels have risen to concentrations not seen for millions of years. And to understand the scale of that, go back to our calendar. In the last 200 years, less than 1 second out of 4.5 billion years, humans have shifted atmospheric CO2 concentrations more than any other event in the last 3 million years, except for ice age cycles. The current rate of species extinction is 100 times higher than the background rate, not 100% higher. 100 times higher. If a geologist of the future examined rock layers, they would find a marker of our presence as sharp and clear as the asteroid impact marker from 66 million years ago. 1 second. And a geological fingerprint like an asteroid, which is exactly why scientists are asking a question that's uncomfortable to hear. Is humanity the sixth mass extinction? And there's one detail that makes that question particularly uncomfortable. Every one of the 5 previous extinctions had an external cause: glaciation, volcanoes, an asteroid. None was caused intentionally by life itself. The 6th extinction, if it happens, would be the first caused by a conscious species that knows what it's doing. The first extinction that could be stopped. And so far, we're not stopping it. We're not yet at a point where a 6th mass extinction is inevitable. There's a whole range of trajectories that extinction rates could follow over the coming decades and centuries. Which one we take is up to us. We started with 4 questions. Time to answer all of them. How many times was Earth on the edge of total destruction? At least 7. The late heavy bombardment, the oxygen holocaust, snowball Earth, 3 times, 5 mass extinctions. And every single time, something survived, something adapted, something became the beginning of the next chapter. How did Earth rebuild itself? Through plate tectonics, the most unique mechanism in the solar system. Through volcanoes that regulated the climate. Through crises that destroyed the old and made room for the new. What forces shaped the planet? Gravity that assembled it from dust. The impact of Theia that created the moon. Tectonics that continuously reshape the surface. The sun that provides the energy. And life itself, which transformed the atmosphere and became part of the planet's own geological machinery. And the final question: why did Earth specifically become capable of supporting life? And could it easily have not happened? The answer: yes. It could easily have not happened. Without the impact of Theia, no moon. Without the moon, an unstable axis. Without a stable axis, a chaotic climate. Without plate tectonics, no thermostat to regulate temperature. Without the right distance from the sun, either too hot or too cold. Without Jupiter deflecting most of the large asteroids, far more impacts. Earth is a coincidence, a lucky one, a rare one, possibly unique in our galaxy. 4,500,000,000 years of catastrophes, crises, extinctions, resets, and in the end, a planet that gave rise to the only civilization we know of in the universe. You are standing on the result of the longest and most complex process we know, on a planet that went through all of it and survived so far.